I'm Gordon Cooper. I'm the Product Marketing Manager for the NXP's LPC 4000 family of parts. The 4000 is all based on the Cortex M4. I'm the marketing intro, if you will, 10 or 15 minutes. I promise not to hit you over the head with too many marketing slides before I turn you over to Paul Bogarts, one of our applications engineers. So he'll go into the meat of the presentation. But I'll give you, if you will, the 30,000-foot view, and we'll kind of walk into and make sure we're all on the same page of, well, what is an M4? And what is an M0, dual core, before we jump into the dual core discussion. So just a quick show of hands, how many of you have used or are very familiar with ARM 32-bit cores, whether it be ARM 7 or okay, so more than last time. Excellent. Well, then this will be very quick. A few you might not be. ARM certainly has the ARM 7 core, very nice microcontroller core. The ARM 9 was more of an application processor. People still buy them. We still sell both, sell quite a few of them. With Cortex M3, ARM looked at a way of saying, well, successful with the ARM 7, but how do we get faster speeds? How do we get better interrupts? How do we get lower power consumption? So really the M3 is the replacement or next generation for the ARM 7. From the M3, they went two directions. They went to the M0 and the M4. The M0 is the M3 with a reduced instruction set, reduced die size, so you get better power numbers. So that really is their attempt to go after the 8 and 16-bit space and really low-end 32-bit microcontrollers. The code of the M0 will run on an M3. The M3 and the M4 are virtually identical, except for the M4, ARM said, well, let's go into that DSP space a little. So they added single cycle multiply accumulate. On the M3, it took 3 to 7 cycles. On the M4, it takes 1 clock cycle. So if you're doing a filter or an FFT, then that's really important to do your fast multiply accumulate, your signal processing. Now you don't have some of the parallelism that you get in a pure DSP, so it isn't a direct replacement if you only want to do filtering. If you only want to do an FIR filter and that's all you want to do, DSP might be a better choice. But if you want to do an FIR filter and USB, or you want to throw Ethernet in, or do any of those microcontroller kind of features, then you should really consider the M4 as a potential choice for you. Now what we've done is said, our M4, if you want to do signal processing, let's let the M4 do that, and let's give you an M0, which we happen to have as well, to do other things like your USB stack. And Paul will go into some of the details of the architecture and how it all works together. We also looked at, from an NXP point of view, 2 years ago, we could have said, look, we have M0, M3, M4. We're focused on microcontrollers. Come to us first. We've had 10 years of history with ARM. For those who don't know, Philips Semiconductor spun us out. So NXP is the old Philips Semiconductor. We started with a bunch of 8-bit parts, completely focused on 32-bit microcontrollers now. We do have some ARM 9 parts as well. So I could have told you, come to us first because we have the whole spectrum of parts. Well, in the last couple of years, there's a lot of people that have M4s that have, a lot of vendors now, a lot of competition has kind of jumped in. So how do we differentiate? Why would you pick NXP? So we have our LPC. If it's LPC, it's our microcontroller. If you think about, there's 3 things that you have. You have the core, you have the memory, and you have the peripherals. And so we're looking at, and we'll talk about today, is some ways that we differentiate. Well, one way to differentiate is core, is we're the only guys with a dual core with 2 M cores. With memory, we have a new interface called SPI flash interface, so that's one way we differentiate. We have dual bank flash, and the dual bank flash is nice because you can give one to each core, or you can do in-application programming, execute from one while you're programming the other one. So there are different ways that we look to differentiate, look to give you choices. And then with peripherals, we have USB, but we have high-speed USB, and we put the high-speed PHY on it for you. Well, I don't think we even talk about that in this session, but that's a way to differentiate. We give you free software for USB, so you can get USB libraries that we give you for free. But there's also configurable peripherals that we'll talk about, very unique NXP peripherals that you can use, and Paul will talk about the state configurable timer to do any kind of timing waveform that you want, serial GPIO to kind of remove the need to do bit banging in the future or to emulate other interfaces. So those are what we'll talk about in this session. However, I'm completely open to questions, and stop us if you have questions as we go along. So LPC, I can't tell you what LPC stands for. It doesn't really have it's an acronym without a definition. But essentially it is synonymous with NXP microcontroller. And we're putting a lot of focus. You might see LPCXpresso as our low-cost development tools, where if you don't need more than 128K of flash, download LPCXpresso for free, and then you don't have to pay any extra money. You can actually go to production with that. If you need more memory, you can actually upgrade to the Code Red, or of course there's Kyle and IR tools that are out there, Atolic, a bunch of options for you. If you want to see some videos, and it's worth mentioning the video camera here, this session is being videotaped, so if you want to refer back or share it with somebody, within a couple weeks this will be on our YouTube LPC Zone channel. So everything we talk about here, videotaped, and then it'll show up there. And previous sessions we videotaped as well, so if you missed the USB from earlier, or you can't make the session on the ecosystem later on today, you can see those via video. Okay? We've grouped our parts hopefully the way that you would use them. So if you look at microcontrollers and say, I just need a vanilla microcontroller, I don't need connectivity, I just need to control some things, that would be in the LPC Go space, if you will. So very low-end 1100 M0 based microcontrollers, or very low M3 would fall there. On the Connect space, you're connecting two things together. So an M0 that has a CAN interface, or a USB interface, or CAN with CAN transceiver. So you're connecting two things together. That would be in the Connect space. On the Connect Plus, you're doing more control. You're connecting multiple things. So now we offer you an Ethernet plus USB, or Ethernet plus SD card, or plus external bus, or plus LCD controller. So if you're connecting multiple things. We actually have a brand new M4 part that's announced today in this space called the LPC 4000. Single core M4, full speed USB, graphical interface, but a great chip if you're looking at it and you don't need the performance of the dual core that we'll talk about today. ConnectTurbo, well, now we crank up the speed. So where we're 120 megahertz here and maybe 50 megahertz here, we're 204 megahertz. So nobody's come close to having a 204 megahertz M processor. And not only have we done that, we've given you two cores. So we've given you the M0 and the M4 that can both run up to 204 megahertz. We give you high-speed USB. We give you some of these advanced peripherals. So what we're talking about today, it falls into this space. But from a price point, this space could be in the $3 to $8 in the 10,000 piece pricing. So very very good pricing considering all the things that you get with it. Command is some ARM9 processors. We don't have the fastest ARM9 processors, but great value for what you get. We also have Linux that supports that, so lpclinux.com. You can go and get free Linux to work with our ARM9 processors if you're interested in that. Okay. And just a little bit of a decode chart for you. So again, we're up in the high-speed LCD, Ethernet, CAN, SD card, fastest speeds, highest integration. So that's what we'll talk about today. Right. Okay, this is bragging a little bit. But the point of this slide is we pride ourselves in innovation. So a lot of the things that we look to do and the things that you'll hear about today are unique innovations that NXP came up with that nobody else has. SPIFI, SCT, the dual core, serial GPIO. And those innovations have often led to recognition and view some of these awards. So the 4300 received an award here based on the 4000, which received a couple awards here. So we're actually proud of the fact, less of the awards, it's a nice to have, but proud of the innovation that NXP looks to differentiate from our competition. So I mentioned the ConnectTurbo, if you will. It's basically the 4300 that we'll talk about today. That's the dual core. But it's worth mentioning that we have a single core M3 with most of the peripherals that we'll talk about today. And that allows you to say, well, maybe I don't need the signal processing or the floating point unit, or maybe I don't need the dual core. Well, here's a pin-compatible M3 you can drop in. Or maybe in your design you have here's my standard product and here's my premium product, if you will. You can base them on two cores, same footprint, same code, same peripherals. And if you would, next slide. So this just shows you a quick overlap. So the 1800 and 4300 that we're talking about today are pin-compatible. And the only differences are M3 and a little bit less SRAM in the flashless part versus the dual core, and the serial GPIO is only on the M4. I mentioned the 4000 that we announced today. Like the M3, the 178X, it basically is just an M4 replacement with the floating point unit and with SPIFI, and we threw in two analog comparators. But again, we give you a pin-compatible migration path. So the M3 is slightly cheaper, not significantly actually, but slightly different price point, and then you can add these extra features if you choose to in a pin-compatible way. But we'll spend our time in this space today. Right? Here's the block diagram. A lot of stuff. Here's your two cores, your M4, your floating point unit, your M0. This is your system stuff. We throw in a couple extra PLLs. Great if you're doing USB synchronization or streaming audio. It says USB and audio, but you can use the PLLs for anything. Timers, we have standard 32-bit timers, but we'll talk about why this SCT takes that to the next level. A motor control PWM that you don't have to use for motor control. It can just be a whole bunch of PWMs. This version is our flashless, and it's worth mentioning we have two versions. We have a version with no flash, and we have a version with up to 1 meg of flash. Now you would say, why would I ever not want flash? And the answer is, flashless is cheaper. It's cheaper for us to manufacture. You say, well, I still want flash in my system, and this is where that SPI flash interface comes in. You can add and make it look memory mapped, and I don't want to steal Paul's thunder. You can add a significant amount of quad SPI flash very inexpensively, teaming up with this part, which has more SRAM, for a much lower price point than the 1 meg flash. So customers have looked at it both ways, and some kind of go one way, some go, well, I really like the price point. If cost is really important, you might want to consider flashless plus the inexpensive quad SPI flash. So we offer both. Whole host of peripherals, LCD, CAN, SD card, external memory bus, USB with a high-speed PHY I mentioned. You can have two hosts. If you want two high-speed USBs, one has internal PHY, the other has the hooks for an external PHY. If you want two full-speed PHYs, full-speed USB, it's already built in for you. So, okay, next slide. This is almost identical, although we've added EEPROM and we've added the 2 banks of flash. The SRAM is slightly smaller, but you get the 1 meg of flash. It's worth mentioning the 4310 is sort of the vanilla part. The 20 adds the high-speed USB. The 30 adds a second USB and Ethernet. And the 50 adds your graphical LCD controller. So depending on what you might be interested in there. But we give you some options. Okay? So this is the board you're walking out with today, the LPC, or the NGX LPC4330 Xplorer. So 30 is to USB and Ethernet. This is the Kyle U-Link ME. How many people are familiar with Kyle U-Link 2 or U-Link Pro? This is like a U-Link 2 without the case, more or less. Kind of the same performance that you'll get. Paul will go into a little bit more detail about what's involved here, but this is everything you need to get started. You can actually go to Kyle, by the way, and say, hey, I've got this. Well, you can download the free Kyle version for 32K of flash. You can call them up and say, hey, can you give me a 30-day license for the full version? And they'll be happy to do that. So wait till you want to use that, but you can get the full version to kick the tires on that. All right. Another board, this is, for us, a flashless version, but if you're interested in the flashless, this is the Hitex board. It has the full flashless part with connections for the LCD, so it's a 4350. If you didn't pick it up, this might be worth looking at. This is the first board we came out with, and the flashless part came out first. So we went out to 10 embedded experts, guys that had been programming for a long time. I don't know if you know Jack Gansel writes some books on embedded development. He was one of them. And we said, here's the board for the part. Here's our software. Here's some Kyle tools. Go kick the tires and tell us what you think. And they each took a little bit of different approach, but this is a summary of their write-up. So very interested to see the kinds of things that they looked at. You know, Jack took an approach that said, well, if I have 2 cores, what does that mean for power consumption? How do I maybe partition the cores? So interesting. All the code, all their project files are available as well. This is a good starting point. So if you're interested, might spur some ideas, or you know, I like the Amazon thing where I read what other people say about it. This is kind of that concept. So read what somebody else said. All right. And then the Kyle board. This is, we're showing in our booth. This is the 1 meg flash. So this is also out. This is more in the, about the $300 range. It has a graphical LCD. It has all the connections on here. So this is a nice little board with the flash as well. So if you want a more high-end board or you want the graphic LCD and flash, this is a good way to go. IAR and EA, Embedded Artists, have boards coming as well. Okay. Okay, this is one of those marketing slides. How many are familiar with Core Mark? Almost nobody. Okay, Core Mark is actually an independent website that allows different vendors to benchmark their core. So if I wanted to compare how good is a core, like an M4 compared to a Renaissance or a microchip part, then it would give me a pretty good indication on a certain score. They give you code that you have to run, and it just gives you a score. Now that works great if you're doing independent cores. Well, how about an M4 versus an M4? Can I really get any kind of comparison? No. If you're running from SRAM, it's going to be identical. If you're running from flash, we used to be able to say, look at our Core Mark score because we have a great flash accelerator. When you want 32 bits, we actually read 256 bits, and it acts sort of like a cache. So we can get near zero wait states when we do flash accesses. The competition is kind of caught up on that. So really, Core Mark is an indication of clock speed or compiler efficiency. So maybe it's interesting to see, well, what did the IR get on the same part as the Kyle, or Green Hills has a version out there as well. So what this just shows is that here's our 180 megahertz M3. Here's the nearest competitor at 168 megahertz. Here's where most of the other M4s are in the 100 to 120 range. It's very linear, as you can see, as I would kind of expect it to be. So here's the 204 megahertz. Core Mark doesn't let you double up when the dual core, so we can't record it that way. But here's where the M0 is. The M0 is not as efficient as the M4, but it's great if you're doing microcontroller type features to handle USB or other I/O performance. So with the M4, the dual core, you get the highest processor for the M space, and you get the M0 on top of that in terms of performance. And it's worth mentioning that really you get at the price point of our competition. Okay, so this is my transition slide. I'm going to hand it over to Paul, who will go into the details on some of these advanced peripherals and the dual core.
Okay, so we're going to talk about what makes our products unique in the, especially in the Cortex M4. Gordon already touched on the asymmetric dual core design, so that is unique to NXP. So let's take a look at symmetric versus asymmetric. So we're all familiar with symmetric, multiple cores, normally you use an OS, and you have shared memory. An asymmetric is like we have on our LPC 4330, which has a Cortex M4 and a lower powered device, a Cortex M0. And they can share the same memory, or generally you would use different memory space for the two devices, so they can both run at maximum speed. An OS is not required. Debugging is very simple, and we'll go into that detail. So the bus matrix helps prevent bus contention. So in this example here we have the Cortex M4 and M3, and we want to make sure that there's no contention on the memory. So the flash is in dual banks. At 1 meg, it's dual banks, so you can actually run the M4 from one of the banks and the M0 from another bank. So in this case, with the bus matrix, they're both running independently, full speed, no contention, no arbitration on the bus. So they're both running at maximum speed. You can do the same thing with SRAM. There's many banks of SRAM, and you can configure them however you want. So you have full access to the SRAM space for both cores. So that allows them to run at maximum speed. So partitioning your application, if you could look back at that bus matrix, is the key. You really have to think ahead how you want to partition your design. Not only your memory, but also your peripherals. So you really want to take a look, okay, what should my M4 be doing? Is it going to be just the number crunching, and then the M0 does all the USB and Ethernet, which it's very capable of doing because it's running at 204 megahertz, just like the M4 is. So you really have to think ahead and decide exactly what you want to do, what you want to accomplish, what each core is capable of doing. And if you do that in advance, you're going to run into a lot. If you really think ahead on that, I think it's a big advantage. Because this actually allows you, because they are separate cores, you can actually have one person working on the M0 and one person working on the M4, because they are separate cores. Now, there are no hardware restrictions when you really take a look at that. I mean, you can set them up however you want, but the way you partition it will definitely make the design and the performance optimum. We also added a peripheral in the 4300 called the IPC, and the IPC is just allows you to communicate between the two cores easily. So you can do it just using interrupts. You can use a message queue, and mailboxes and queues, and a lot of that's done in ROM for you. You can just use interrupts if you want. So you use a set event command to tell the other core, okay, I'm going to send you some data, or you need to process some information. And that goes both ways. So you can interrupt each of the cores. Or you can create a buffer. And if you take a look at the host command buffer, the M4 can only write to it, and the M0 can only read from it. And on the host message buffer, the M0 can only write to it, and the M4 can only read from it. So this is a nice way to ensure that data is not overwritten by either core. So that's a feature that's available. It's not required to use it, but it's just to make your development a lot easier. And there is an application note available, very good with example code on our website. Dual core development. What makes this unique is that you really, both cores are actually on one JTAG chain. So you can actually, with 2 instances of the IDE, debug both cores. And what I'm going to do is I'm going to show you an example of this. So I have the same board that you have, so the Ulink ME debugger. And we're going to, for power, we're just going to plug it into one of the USB ports. Doesn't matter which one. Okay, and what we're going to do is there's 2 LEDs on this board, and one is going to be controlled by the M0, one's going to be controlled by the M4. I'll kind of hang that over, and hopefully you can see it. Okay, so here is the, hopefully this is the M4. Okay, so it's talking to it now. And I'll start running the code. It popped out of debug mode. Let's start that one again. Okay, so we can see the core is running. And if I pull in the M0, start debugging, you can see that we have both the amber and the blue LEDs being lit. Now I can stop the M0, right? You can see the M0 and you can see the amber LED is stopped. So I'm controlling the M0 with one of the IDEs. And I can restart that, and then I can go over here, and the blue LED is now off. Okay, so we're debugging both cores using one Ulink ME. So debugging is really, really, really simple, and you only need 2 instances of the IDE. Here's some how we envision a person would partition their application like for an audio processing application. So for audio processing, you probably want to use your M4 fully devoted to audio processing, while the M0 can easily handle all the I2S and USB. So they won't be taxed at all doing this sort of thing. So where to go next? A good place to start is, first of all, is you always want to go to our LPCware site, okay? LPCware is the site that we place all our driver libraries, app notes, like NXP USB Lib, our MWin graphics library. So that's a very good place to start when you want to develop anything on an NXP microcontroller. So we have our things like our PDLs, peripheral driver libraries, again, all on lpcware.com. The boards that you're getting today, there's a lot of good examples on the NGX website. Okay, so if you go to NGX, they'll have a very nice selection of different projects you can run using their code. Okay, so the SPI flash interface. So Gordon touched on this. We normally call it SPIFI. The advantage of this peripheral is that it saves you board space versus NOR flash. SPIFI can actually execute in place. So even though it uses serial, it can execute in place and it's got very good performance. You can boot from SPIFI if you want. So these boards that you're getting today, even though they don't have internal flash, they have SPIFI and you can boot from SPIFI. And we'll take a look at some of the Core Mark performance that we've achieved with SPIFI. So again, it's a 6-pin external interface, patent pending, allows designers to use small and inexpensive serial flash in place of larger, more expensive parallel flash, or internal flash for that matter, right? Because internal flash is very expensive compared to these very inexpensive flash devices that you can purchase. A key feature of SPIFI is that the bottom bullet you'll see the external serial flash appears in the memory map. So once the microcontroller queries the SPIFI device, it'll actually read the manufacturer and vendor information and say, okay, I know what you are. I'm going to map you into my memory map. So it won't know the difference between internal flash and SPI flash. It considers that part of its memory map. So you can execute in place, you can use it for storage. So that makes, again, for the life of the developer a lot easier because you don't have to worry about external memory controllers and things like that. So here's shows you significant savings in board space. I think it's kind of obvious. You have obviously a parallel flash device. You're going to use a lot of pins. You're going to use a lot of real estate versus the 6-pin device. So we already talked about this. There's a 64 meg space where you can play SPIFI, and there's also a second 128 megabytes block of SPIFI. You can actually put the memory in either of those locations. The advantage of using this one is you can actually debug from this one. For some reason, you can't debug from the second one. So you don't have to execute from it. You can also use it for image storage. So if you have a lot of images and you have an LCD, you can just store your images on SPIFI. And the nice thing about that is the high-speed quad SPI flash interface is supported by DMA. So you can DMA directly from SPIFI to your LCD. And there is an app note on that using the SPIFI as an LCD frame buffer. And that URL is shown at the bottom of the slide. Here are the SPI flash parts that are currently supported. So when we first developed this, we went to all the major manufacturers and they gave us samples of the parts that they had available. Since then, I think they've added a few higher density parts that are not currently on the list. But you can still access those parts using SPIFI calls. So here's an interesting one. So you would think that SPI flash wouldn't be as fast as an external SD RAM or external flash. But when you take a look at quad SPI flash, it's obviously not as fast as internal SRAM. So If you're running the part at 204 megahertz, your interface is obviously 204 megahertz. There's no wait state. Your core mark's about 2.15. Using quad SPI flash, your CPU frequency running at 204, your SPIFI interface running at 102, you're going to get a core mark of 1.22, which is pretty good when you compare it to 16-bit SDRAM, which is a core mark of 1.03. Again, that's 16-bit. If you had a 32-bit interface, the SDRAM is going to be a little higher than the quad SPI flash. But again, you're talking a lot more pins. And the 16-bit NOR flash is extremely poor on the core mark score. So when you take back, what you want to take out of this is internal RAM is fastest, internal flash is going to be second, quad SPI flash is going to be next, and then external SDRAM or NOR flash. You want to, if speed is the option, you want to take a look at those last. Now, all these measurements were taken using Kyle Microvision. We have done some core mark benchmarking with Green Hills, and we can actually achieve a little bit higher scores with those. But this gives you a good general feeling for the relative speed of the various interfaces within the part. So again, refer to App Note 11206 and using SPIFI on the LPC 1800 and LPC 4330 devices. We can actually show running from SPI flash. I can see this. And this is, so what we have is an audio source, which is my phone. That's not going to work today. Oh well. Anyway, if you pull up those NGX examples, you'll be able to. What this example shows is it takes the audio in from an audio source. The codec turns into I2S, and then I2S back out to the codec to an external speaker or headphones. So that can easily be done using the boards you're receiving, and that's running out of SPI flash. Odd. Oh, I guess you have to turn it up. Okay, so certainly SPI flash is capable of running some good applications. So next on the list, SCT, which is the state configurable timer. So what is the SCT? So it's a timer with also a state machine built into it. So it's a timer enhanced by, there's input capture events, signal out capabilities, interrupt and DMA events, a state machine which defines the behavior of the counters, outputs, interrupts, DMA, and other features, and a lot of interconnection between these. The key features are there's 8 inputs. Those don't have to be 8 inputs on the pins. Those can be peripherals as well, internal to the part. There's 16 outputs. There's 16 match capture registers, 16 events, and 32 states. Here's a block diagram. The left side is fairly standard timer, but if you look on the right-hand side, you have our outputs feeding back into the event generation. You have state logic, again, all feeding into this event generation, and again, which can also trigger DMA events. So I created a very simple example. So in this example, what it has is just the two LEDs on this board, on your NGX 4330 board that you're going to get today, just blinking. So those are the two states on the right, so turn on and off. Also has an input or a reset input, that's L always. So that's a state that, it's a pseudo state that gets executed from anywhere. So no matter where you are in that state diagram, you can always pull it back to L always. So in this case, we're using it as a reset input. And then there's an entry point. So very simple to use this. Now this tool is built into LPCXpresso. And if you're not familiar with LPCXpresso, it's our free IDE. It's an Eclipse-based IDE. Code is, it's free for code up to 128 kbytes. And it's actually developed by Code Red. And if you want to go above 128 kbytes, they have a migration path to incrementally increase the cost if you want to go up to, let's say, 1 megabyte or 512. But again, it's a very nice tool. And this has the state tool built into it. So you can use the state tool if you want to use Kyle or IAR and easily just create the state machine in LPCXpresso. And then all you have to do is at the bottom left, there's a button called Generate Code. So every time you make a change in your state machine, you just generate the code, and it'll generate 4 files. You take those 4 files, and you pull them into your other project that you're working on. So using this is very, very simple. And it's all done graphically, so you don't have to worry about all those registers, because there's lots of registers for this peripheral, and this makes it very, very simple to use this peripheral. So I just got this morning. I think it's a pretty interesting implementation of a camera interface using the SCT. I always thought that we would use the SGPIO, which we'll talk about next, but certainly the SCT is fully capable of being used as a camera interface. And so basically what you're going to do is you're going to take 8-bit data and just connect that up to GPIO. And then the SCT itself, here's the SCT, is going to be looking for trigger events like your vertical sync, your horizontal sync, and your pixel clock. Every time it sees a pixel clock, it's going to read the data and DMA it into your buffer. And you can do some processing, and then you can throw it into your frame buffer. So if you look at the state diagram for this, you initialize, you're waiting for your vertical sync, and you get your vertical sync, and then you should get a horizontal sync. And then you should end up in this INH event here. And every time you get a pixel clock, you get a DMA request. And your DMA is going to take that 8-bit data and throw it into your frame buffer or in another buffer where you're going to do some processing on it. And then the only time you get an interrupt is when you get the horizontal sync. So you get an interrupt right here. So you take a look at it for a 640 by 40 at 30 frames per second, you're going to get 14,400 IRQs per second, and you're assuming approximately 100 cycles required to service that IRQ, and for 100 megahertz, if you're using this on the LPC 1800, it's less than 8%. So most of the work is done automatically by the SCT. So here's an example of how this configurable peripheral can do very specialized interfaces like a camera interface. Other use cases, obviously motor control. Anytime you need PWMs or things like that, PWMs are obviously trivial using a device like this. Lighting control, generation of custom control signals and hardware, custom sampling of input signals, frequency detection, pulse width detection, phase detection. And there, we do have an app note, which describes how to use the SCT and then how to migrate if you're going to be using like other tools, other IDEs like Kyle and IR. Serial GPIO is probably the most complex of the peripherals we're talking about today. And again, how we envision people using this is for data stream processing or protocol emulation. So GPIO is just like it sounds like, it's a GPIO plus a timer shift register. And it's used to create or capture multiple real-time stream data. So you don't have to write code with loops to manipulate GPIO in real time. So no bit banging, which of course takes a lot of CPU cycles. The key features is there are 16 input outputs, each with their own timer shift register unit. A counter control the rate at which the clock data is clocked in and out. Counter to control the number of bits clocked in and out. And the output has 3 states, high, low, or high impedance. Okay, so the key features. So we said there were 16 SGIO, we call them slices. And so each slice is made up of a counter, and the counter is a prescaler, so you can scale the clock down, and a position counter, so you can decide how many bits are going to be sent out, 8, 16, 18, or whatever you want to send out. It also has a register that you're shifting and a shadow register. So as soon as this position register hits 0, then the shadow register is automatically shifted parallel into the shift register. So this is all done automatically. So you just set the counter, the position counter, and then you're just feeding data into the shadow register. We already gone over this. This peripheral is controllable by either the M0 or the M4. So again, going from a bit banging approach where your CPU is fully utilized, just toggling the bits and timing events, SGPIO you just set it once and you'll get an interrupt when the 32 bits or whatever you need is sent out. You can actually concatenate the registers as well, so you don't only have to do 32 bits, you can actually concatenate them into longer strings. So that leaves your CPU free most of the time. So what can it do? Well, we've already shown that we have an app note on our website already that does SPI. So that the app note and source code is available on our website. We know that it can do quad SPI flash as well. It can do I2S. We've actually shown that in an application, in a 7.1 audio application. And it can do I2C. But again, there's really no limitations with this peripheral. So here's the 7.1 audio application. So the SGPIO is doing the 7.1 audio. The M0 is connected to the SGPIO. The M4 is doing all the audio processing. And the high-speed USB is coming out from a PC. So the M0 is handling all the interrupt-intensive I/O processing, while the M4 is available for audio processing and filtering. It can also do a camera interface. The SCT can do it. This can do it as well. The interesting thing, the CPU load on it is about 35% when you're running 150 megahertz on the Cortex M0. So where to go next? Always go to LPCware. Again, we'll reiterate that again. LPCware is where you want to start for any kind of information on microcontrollers. So we do have the SPI master emulation for the SGPIO peripheral. We're working on the UART, PWM, I2S emulation. We already have that working. And the video interface, we have that working as well. It's just a matter of documenting it and putting it up on our website. And there's a lot more to come. And we're hoping our customers will come up with a lot of new ideas.